join me to welcome Dr. George Turkiyyah, a research professor at KAUST, specializing in computational science, HPC, and AI applications. Previously, Dr. George served as a chair of computer science at the American University of Beirut. He was also a faculty member at the University of Washington, and he holds a PhD from CMU. He won multiple awards, has several patents. Please join me to welcome Dr. George.
Thank you very much. Thank you. It's great to be here. I think people are still walking in. You missed the energizing session, those of you who are just walking in now, but it was fun. Thank you, Rania. So my talk today is sort of optimization. And I sort of subtitled it the workhorse of machine learning. And I really believe this is sort of what makes optimization so important, because it really underlies everything, as I'll talk about in a couple of minutes. So, so my talk is in 3 parts. The first part is why. Why do you even care about optimization? This will be very short, just a couple of minutes. And then I'll do a quick sampling, very quick, just a few minutes, also sampling of machine learning optimization problems, because every machine learning problem is an optimization problem. Do a quick sample just to sort of get a feel for things. I did not want to spend too much time on this, even though that's really often the fun part of doing work, is try to formulate an interesting machine learning problem as an optimization problem. Nonetheless, I think I'm going to focus more on sort of some of the big ideas in numerical optimization, the ideas that have really made modern AI possible. And along the way, we'll talk about some of the missteps, why for a while it didn't look like this was promising, and why it wouldn't work, and why in the end it worked. So let's start with the first point, why? Why optimization? And there are really 2 reasons. They're a bit intertwined, but they're sort of 2 distinct reasons. One is every machine learning problem can be formulated, or often is formulated, as an optimization problem. That's not at all obvious, actually, because of the generality and the compactness of the way we formulate optimization problems. It's not always clear that every machine learning problems can, but in every context, whether supervised learning, semi-supervised learning, where we make up some tasks to train our models, or whether just unsupervised problems, every time we're going to be minimizing some interesting function, some loss. We want to maximize some reward. And often our task is to figure out what are the decent rewards or the decent losses that we can write that will optimize well. So we build our rewards or our losses with the optimization in mind. And I'll mention, because many of the failures can be understood as failures of optimization more than anything. So examples of classical machine learning problems that can be readily formulated as optimization problems are things like, logistic regression, clustering, just, deep networks, some classifiers in the end, some loss at the end, dimensionality reduction, regularization, how we can improve our classifiers by adding terms to our objective. I'll say a few words about this. Support vector machines. These are more traditional things, support vector machines and others. The sort of parameterized machine learning models. But certainly the big success of AI has been in the parameterized models. So, the diffusion models, you're going to hear about diffusion models in the following lecture, sort of maximizing the likelihood there. It's a beautiful optimization problem. Reinforcement learning, we saw some of that earlier today. Sort of all these problems in the end are formulated as optimization problems. So, so that's one reason, is everything, so we can have that sort of unifying structure. So algorithms, therefore, from numerical optimization. And numerical optimization really predates modern AI. Numerical optimization is as old as computing, almost. So AI has used and exploited the powerful algorithms of numerical optimization to make learning practical, really. So this is a big success of machine learning, comes because it's sitting on the shoulder of numerical optimization. So why should we study then numerical optimization? Because these are, unfortunately, not just black boxes. Even though they give us a unifying structure for a lot of things, often these algorithms fail. So we need to understand, why these algorithms don't work, why sometimes our networks fail to train, why they converge slowly, why they are unstable. All these sort of failures can often be directly explained by the behavior of the optimization algorithm. So it's often not our model that's the problem. The model has the capability to learn, but our optimization is not able to produce that outcome. And that's the problem. And that's why sort of studying numerical optimization is important. So this talk is really just a little briefing for those of you who have not sort of invested a lot of time in optimization. It is worth investing the time because of these two reasons. Every problem of machine learning is written as an optimization problem, and our underlying algorithms allow us to understand why things don't work when they don't. And often they don't. So we often blame, we don't have enough data, or our model is not capable enough, or we need some. But really, in the end, understanding these failures through the lens of optimization is what gives us a lot of insight into the problem and allows us to remedy the failures. So a couple of quick examples, just a few minutes on a few examples of problems. Many of you may have seen this, but if you haven't, actually, I think it's good to appreciate that. So let's take the problem of clustering. Do I have a pointer, by the way, here? Can I point to something? No? Okay. So on the top right, you see cluster of points. I would like to be able to cluster them, let's say, into 3 clusters, the red and the blue and the green points. I want to do that. So this is, everybody has done the clustering, the first exercise you do in any kind of machine learning course. But often what we don't do, we don't write it explicitly as just a one-liner, elegant optimization problem. And I think it is that abstraction, being able to write this problem as just an optimization problem, is where we get some insight into what's going on. So every optimization problem, the first thing to do is identify what are the parameters, what we call optimization variables in traditional lingo. What are the parameters we're trying to find, to assign values for? And then what is the objective function? Objective function is the term used in the traditional optimization literature. And in machine learning, we call it loss functions or reward functions if we're maximizing or whatever. So, so the problem really is to minimize some loss function, some objective function, and we want to find the optimal values that minimize that function. So for example, for this clustering problem, the first thing to do is to figure out what are the optimization variables. What are the variables who, when we assign values to, we've solved the problem. So there are 2 things. We want to know, let's say we want to divide the set of points into 3 clusters. I want to know for every point what cluster it belongs to. So I need maybe a vector of values, a vector of classes, vector of colors. This is a vector C here. It is of the same size as the data, and each value is going to be 0, 1, or 2, depending on which cluster it belongs to. I'd like to know what these values are. And then maybe I need to find some cluster representatives, some centroids or whatever, and the coordinates of these will be Z. So a vector Z of 3 locations and a vector C of the size of the data, these would be my optimization variables. So that is often the first step in sort of really formulating the problem. And then I need to figure out what is it that I want to minimize. And it turns out I'd like to make the design clusters. One way to design clusters is that I want a bunch of points to be close to their center representatives. I'd like to maximize that. And this will be done by minimizing this function J here. It's the sum over all the points. And you see sort of X sub I, these are the data. These are the black data points. These are the features for every point of the ith data point at least. And the Z is subscripted by these unknowns. And this is a beautiful optimization problem. We sort of know this actually happens to be NP hard, but we have very good heuristics for solving it. Those of you who know about EM algorithms or whatever, I mean, you probably know how to solve this. And this is, K-means can be understood as one of the many algorithms that we can use, for example, to solve this problem. There are many variations. Spectral clustering, for example, which often was needed to be able to cluster things that may not have convex kind of clusters, can be written exactly in the same form, where we replace xi by their spectral coordinates. So we build this matrix, this distance matrix, compute its eigenvalues, project on the eigenspaces, and then use those coordinates, and we write the same optimization problem. So, and I'll go quickly through the others. So linear regression, of course, our goal is to figure out some values of parameters. There will be, the weights and the biases of our fit, and then we're going, this is a least squares problem. problem. In fact, this particular problem has a closed form solution. So we can write it as an optimization problem. This is this is as old as Gauss, I think, wrote the least squares problem. And we can solve that. And of course, theta are the unknowns here. These are the weights and the biases. Y is the data that we're trying to fit. And A is, the columns of A are sort of the features of our data. And then if we do classical feature engineering, we can add more columns. Dimensionality reduction is a beautiful problem. You see on the bottom something, the structure of it. So we have some x's on the left. We're given a bunch of data, bunch of MNIST images, bunch of facial images, bunch of whatever things. And we'd like to see if these data can be represented in a space of a smaller dimension. If there is some underlying latent space that is smaller than the visible space of whatever, of the images we're given. So x's are the images, z's, I'm sorry about the color contrast here. So these are the representations of our images or pieces of text or whatever in some latent space. And the question is, how can we find that? And there are many ways of doing this, of course. And in fact, this picture, if you replace the W and the W transpose, which are sort of, these are linear kind of projections, if we replace them by deep networks, you see the structure of an autoencoder. And you probably know about variational autoencoders and stuff. But this is sort of the first version of it, where we want to build a latent space using a linear projection from the high dimensional space to the lower dimensional space. So again, the question here is, what are the optimization variables? That's always the first thing to ask. What are we trying to find? And then what kind of loss function, what kind of objective we want to invent whose minimization will give us what we need. So for example, here, without thinking too much about it, I think it's sort of obvious. Well, that what we need to do, if you've seen this problem before, we need to figure out what is this decoding matrix W that when we multiply any kind of latent representation with, so W times Z, that should give us the representation in the ambient space, and we'd like that to recover the original, we want that to be faithful to the original data. So the difference between X sub n, this is one of our images or whatever, or video sequences or whatever, minus WZ, this is what we reconstruct, the difference between them should be minimized. So minimizing this is a solution. So and this problem is readily solved. In fact, we have a closed form solution for this, you may know, via single value decomposition. Logistic regression is another problem. We're given a bunch of features, D features for data, and we'd like to predict the probability of being a 0 or 1 logistic classifier. So again, the unknowns are going to be the weights and perhaps a bias in our logistic classifier, and our loss function is going to be how well we're predicting. And again, cross entropy is a typical thing to do. One can do other things, but this has become, cross entropy has beautiful computational properties of convexity and other things that we love to use it, and it's easy to use. And we build J of theta. And you see the unifying structure to all of these. All we're doing is we're writing a loss function in terms of parameters. We identify the parameters, we build the loss function. The multi-class logistic regression is no different. We have a bunch of weights and biases. This is sort of one, you probably recognize this picture as one layer of a deep network, and indeed it is. That's what a multi-class logistic classifier is, and the problem, the formulation of the problem is no different than what I've done before. If we have a multi-layer networks, some deep network, again, the evaluation is on the right. You see the very last layer is some kind of probability distribution obtained by some softmax function at the end. And so the parameters are the weights and the biases of the various layers. These are linear layers. And the loss function is how well we're predicting the given data. So it's a supervised context. We're given data, we're given labels, and how well we match them. And we want to minimize that loss. And then, again, writing that function gives us a lot of insight when things don't work. Let's say a few things about this is what tells us why things don't work when we write them like that. Often we add to our obvious loss function additional terms that are not data dependent, additional terms that we want our parameters, we want our model to respect. So for example, we don't want our model to overfit. And overfit is often attributed to the fact that many of the coefficients tend to be very large in absolute value. Some very large numbers and some very large number and negative large numbers and positive large numbers in absolute value. So one way to actually fix this problem is to add to our objective function a term. You see here it's multiplied by lambda. Lambda is some hyperparameter we can tune so that our parameters are not very large. That term is going to discourage parameters from being very large, from basically overfitting to the data. And notice that this term is not data dependent. This is something we want the model to satisfy. This is the weight decay. If you added weight decay in your software, that's what this is. We're adding this very simple quadratic term to our objective to do this. Quadratic terms turn out to have some problems, so we often become a bit fancier, and what we add are one norms. So on the right column here, you see this lasso regularizer. So the term is not the L2 norm of the weights, so we don't want to square these parameters. Rather, we're just going to add them in absolute value. And that turns out to have the features that this is an approximation. Don't have time to go into the details of this, but this sort of approximates sparsity. So what we're saying here, by adding this term to the objective, we would like our model to use as few features as possible. So sort of it's feature selection in some sense. So here the result of our classifiers not only give us a classifier, but they also tell us what are the most important features of our data, and that's useful. And these ideas can be extended to the multi-class regression in sort of straightforward way. All right, let's, and I can go on and on and on, but I won't. So I'll talk about, what are the sort of big ideas in optimization and what's the problem with optimization. And importantly, when we're stuck, what can we attribute that failure to in the optimization solution? So a quick review. This is what you know from high school is we have a minimum, this X star. So X here are the parameters I'm trying to find. These could be my biases and weights. These could be my latent space representation and the decoding matrix. And these could be, whatever the problem is, the cluster representatives and the assignments of the points to clusters, whatever these are. Generically in optimization, by the way, we call them X's. In machine learning, we tend to call the parameters theta. So you see this depending on which literature you're reading. So in traditional optimization literature, X is the unknown. These are the parameters. That's what we're trying to find. Of course, we know the derivative should be 0 and the curvature should be positive. That's sort of this is in high school from simple Taylor expansions. Of course, this idea generalizes very readily to the multidimensional case. When the set of unknowns I'm trying to find is no longer 1, but maybe 1 million or 1 billion. Modern LLMs are a few billion parameters, and we're going up to trillions very soon, but there's still a vector X. So I need the gradient to be 0. That's what generalizes the first derivative, and I need the Hessian to be positive definite. So if I want to find the minimum of this surface, so think of this colored surface on the top right as being my objective function. That's my loss function in some high dimensional space. Here I can only draw it in 2 dimensions because that's the only thing I can draw. But in our mind, this is meant to sort of tell us this is a function in a high dimensional space. I'd like to find the lowest point in that surface. So that's what I need to find, the point where the gradient is 0. Gradient is 0 is where all the derivatives are 0. So some simple things here, notion of directional derivative, the gradient vectors. The important point perhaps is the last one, is the gradient vector, and it's not that hard to show, that the gradient vector points me in the direction of steepest, oh, this is wrong, it should be steepest, ascent, no, it's correct. So the gradient points in the direction of steepest ascent. So therefore, if I want to go in the direction of descent, perhaps I could reverse that gradient and move in the direction of gradient descent. Of course, which means I need to compute the gradients. Gradients of what? Gradients of our objective functions, of our loss functions with respect to all the parameters. And this is not a trivial task because my objective function, my loss function, my reward function could be a function of billions of parameters. So we need an automated way of computing the derivatives. And it turns out, and this is really the idea that has made machine learning possible, that we can compute gradients automatically. In fact, if you look at the code in PyTorch or whatever, the core code really is an automatic differentiator. That's what PyTorch really really does. Everything else is gravy, and then just making it easy to use in applications. The core scientific, numerical, computational kernel of it is this ability to compute gradients automatically. The famous algorithm is called backpropagation. The idea is we take a function, this is some function j, in terms of parameters theta, and the data xy, for example. This is any particular example. We expand this function. If you're a computer scientist, you've taken a compiler course or something, you can expand this function as a computational graph. Often that takes a lot of memory, and this is why backpropagation consumes a lot of memory. If you monitor sort of the memory usage during training, it's computing the gradients that's excessive, because we have this large computational graph that's expanded. On the bottom, you see it here. It's a chain of computations. We give some data x, and then we compute a linear layer, maybe a ReLU function, maybe, and then we compute some loss, some squared loss or something. And then we want to compute the derivative of j with respect to all the parameters, theta 1, theta 2, theta 3, or whatever. Let's focus on the last line on the right column. So I want the gradient, in this case it's going to be the gradient of j, the loss, with respect to theta 1. This is one of the early parameters. You see, if application of the chain rule tells us this is the gradient of j with respect to x4, then the gradient of x4 with respect to x3. But x4 is a vector, x3 is a vector, so this gradient really is a Jacobian matrix. So we have dx4, dx3 as a matrix, another dx3, dx2, another matrix, dx2, dx, the d theta 1 is another matrix. So we're doing basically matrix vector multiplication when we're accumulating these gradients. And this is done all automatically for us. We take an expression, it's a computation, it's a function, and I expand this computational graph, and then I can work backwards through it to compute dj by d theta 1. I first compute dj dx4, that's the first step, then dx4 by dx3. Notice I'm walking backward on the graph here, and this is the function backwards you use in PyTorch. It's doing all of this automatically for us under the hood. So back propagation, I did 9 minutes, right? Yeah, 9 minutes, is that? Yeah, is that the thing? Okay, so yeah, I'll be done in 9 minutes. So we'll skip backpropagation, but backpropagation really is the key, and the big idea of it is we're walking backward through a graph, and the downstream gradient is going to be whatever upstream gradient we have times the local gradient. We know how to compute local gradients, and these things are chained together very well. So gradient descent has been the main method used for optimization. It kind of makes sense. I want to go down a valley. How do I go? Well, I'm at some point. I'm initialized somewhere. What do? I want to find some direction I can descend in, and then walk by some distance in that direction. Now, what direction should I choose? Well, it may seem like a negative gradient seems to be the right direction, right? Because the gradient is an ascent direction, negative gradient is a descent direction. And this is not always the best direction to take, but this is sort of one reasonable thing to start with, and this is what most algorithms today do, with some modifications I'll talk about in a second. And then we'll pick a learning rate. How far do I want to go in that direction? And then I move in that direction. And I keep repeating this. It's the simplest algorithm one can think of, almost. And you see this picture on the right here. I start at some point, you know, it's high on in this landscape, and my goal is to find some minimum, some local minimum to converge to, and I'm going to take steps. Each step is in some descent direction, maybe a negative gradient, maybe not, and then I move by some direction. So by some distance in that direction, by some learning rate in that direction. And the question is, what is the proper learning rate? We can start with something fixed, and of course, what is important is to decay that, and I'll say a few words about this in a minute. Now, the gradient direction, by the way, is not always a good direction, depending on the problem. So we need to understand a little bit about the conditioning of our problem. This is a little cartoon of these contour lines of an objective function. And you see when the contours are very elongated, if I move in the direction of the negative gradient, I'm actually moving almost orthogonal to where I need to go. So when the problem is poorly conditioned, the negative gradient is a horrible direction to move in, and I will converge very, very, very slowly. So luckily, many interesting machine learning problems are not poorly conditioned. They have a set of contour lines that look like the top left, where actually the gradient direction points me toward where the minimum is, but many are not, and this is important to appreciate. Now, sometimes our loss functions, we often write them as depict them as these smooth functions. Sometimes they're not, but all these ideas can be generalized, and the notion of subgradient has become a very powerful theoretical idea, and all the results we have on convergence and rates of convergence conversions from the smooth case generalized to the non-smooth case with no difficulty. And in fact, this is all hidden for us under the hood. Now, one of the interesting questions is that if you look at this figure in the middle, this is the lost landscape. This is from a two-dimensional section from a Llama 3 model. This is a 1.2 billion parameter model. This is a two-dimensional slice of that loss function. And if you look at it, you probably think there is no way I can converge to the minimum I want to go to. There are lots of local minima. Remember, when I'm converging with the gradient descent, I move, and as soon as my gradient is 0, I'm stuck. I no longer move. So if I look at this picture like this with lots of local minima, this very noisy figure, it's actually, we should be stuck. We shouldn't be able to learn. And in fact, this idea really probably, this thought actually delayed the progress in machine learning by probably a decade. Jeff Hinton said, you know, we can never converge in a landscape like this. But it turns out this picture is actually quite misleading. I mean, lots of interesting work on this recently. And the reason it's misleading is because the space, remember, is a billion-dimensional space. I'm looking at the two-dimensional slice of it, and I see noise. However, there are many other ways of sort of going around. And just to illustrate this idea, I'm showing on the bottom here, bottom right, is a landscape in 2 dimensions, only 2 dimensions. And on the left are one-dimensional slices of it at different parameters at different parameter values. And you see that the contour line the landscapes look very different. So it turns out that looking in low-dimensional sort of projections of high-dimensional spaces is a bit misleading. High-dimensional spaces, by the way, are actually a bit unintuitive sometimes. You probably know the famous result. If I take 2 vectors in a high-dimensional space, they're orthogonal. You know, in all probability, they're orthogonal. But in low-dimensional spaces, if you give me 2 random vectors, they're not going to be orthogonal. So lots of our insights, both visualization and computational, do not generalize. So the good news is we actually rarely get stuck in local minima. We often do not. This has not been a big problem, and this has allowed us to actually move quite a bit. I think it's an interesting sort of reason. Of course, the main workhorse of machine learning is not gradient descent, but it's stochastic gradient descent, where I, rather than computing the gradient, which is the sum over all the data in the supervised setting, I could just take one data sample or a small mini batch of data and use it. Of course, that means I don't get a gradient, but I get an unbiased estimator of the gradient. And this is the reason why, because we use stochastic gradient to move, when I move not in the direction of the negative gradient, but in some direction that in expectation will be the negative gradient. This is the reason why we want to decrease our learning rate. Because if I put you at the minimum and you compute a stochastic gradient, it's going to tell me to move in some direction. So I really, when I converge, I want to make sure I have 0 learning rate so that when I get to my minimum, I do not move anymore. Gradient descent can be slow, and it has been sort of accelerated quite a bit in the last decade, starting with momentum methods. Momentum methods say, you know, I want to go down this valley. One way to explain momentum methods is to think of the point that is the solution of my optimization problem, to think of it as some kind of mass that is moving down this surface. So that mass has some weight. This is that mu parameter here. And then there is a second derivative. So this looks like mass times acceleration. And this is a ball, basically, of mass mu moving under that potential and under some friction. And it turns out if we just rearrange these terms, we'll get what's on the bottom, which is the parameter update is in the direction of the gradient plus an additional term. This additional term tells me how I moved in the previous step. So think of this k plus 1 minus xk, my last iterate, and then where I am now as sort of the velocity, and I can continue this. And this turns out to, if you look at the picture on the right, it's very telling. The stuff on the red, the path on the red, is the gradient descent, but the one in black is where I add momentum. And of course, we can accelerate this momentum very nicely. And then lots of interesting improvement have been done recently where we don't need to update all our parameter by the same amount. Who says we need to update all our parameters in the same amount? Could be some parameters need to get updated more, and this idea of keeping track of what the values are and monitoring them has been incredibly useful in practice, and this is actually what has made Adam one of the fast optimizers out there, because it incorporates ideas both from momentum and from this adaptivity, being able to monitor the values of the gradients, of the most recent gradients, in fact, and rescaling the learning rates to that. There are lots of interesting pathologies in ML. I'll only talk about one of them, the very first one, the vanishing gradient problem. The vanishing gradients are the problem, is the problem that has taught machine learning for years. Because when our gradient is 0, and if you remember our previous slide where we computed dj, the gradient of the loss function with respect to an early parameter, we needed to multiply a bunch of matrices together. If these matrices are small, if they have a small singular value, and I multiply them together, I'm going to get a very, very, very small vector. And that small vector is going to prevent learning those parameters. So this is that insight that comes directly from optimization that allowed people to either change. It's lots of reasons why this happened. So ReLU was invented and was found to be practical, mostly because its derivative doesn't go to 0 on the positive side. If we use a sigmoid, all the early days in machine learning, sigmoids were used as the activation functions, and of course, they saturate, they have 0 gradients, we can never learn. So ReLU was invented, and residual connections and normalizations, and all of these were problems to fix the obvious pathologies in this. I'll finish here saying, so there are lots of interesting problems to be solved in machine learning. One of them is sort of first-order methods, gradient methods are wonderful, but we can do a lot better. We can use some curvature information, some second-order methods to help with that if we can make them computationally practical. So models are great. They define what's possible, but really it's the optimization is sort of the workhorse, what tells us what we can do, what is achievable, what are the things that we can really learn. Thank you.
Thank you, Dr. George. We can take a few questions. Yes.
Hello. Thank you for this great talk. Actually, I have a few questions. Okay. One question, then. Okay, I don't know which one is the best, but I'll ask the first one I have in mind only. Like in the over-parameterized setting, like the new LLM architectures, how can we practically think of the flat minimas? Like, as you mentioned, it's not easy to detect the sharp minimas. How, practically,
very good question.
It still possible to consider the flat minima as a metric or something?
Absolutely, absolutely. Thank you for the question. The question is, can the loss of the shape of the landscape tell us anything about the generalizability of the model we learn? And it turns out that, yes, indeed, if we are stuck in a very deep valley, then we're not going to generalize well. So we would like to converge to sort of a flatter part of the space. I had a picture on this in an earlier version of the slides. But so the question is, can the optimization be encouraged to converge to a flat minimum? And the answer is absolutely yes, because this is related to the sharpness of the point we're at is determined by the largest eigenvalue of the Hessian of our loss. So we can actually minimize that. We can encourage that not to be too large. So yes, indeed, and people have tried to do this and have done that, and it's still an active area, and this can be done at scale, it turns out. Computing the largest eigenvalue of something of size billion, it actually is not too difficult, believe it or not. It looks initially insurmountable, but with these randomized methods, so we can actually do it during training. So yes, we can encourage better convergence to better minima, better in that sense of they generalize better.
So from an optimization perspective, do you agree with the statement that says loss functions are something very important to consider on the path to getting better intelligence? Or, for example, would you prioritize scale, for instance? So what do you think is something that, from an optimization perspective, is highly important to achieve a better level of intelligence?
Yeah, you know, the most impact, the questions about loss functions, you know, is this what intelligence is? Really, loss functions are things we invent. In fact, the most impactful papers have been the insight into what is the loss function that we want to minimize to learn. So it's a proxy to learning interesting things. If you've, I don't know, paper on contrastive learning, for example, if you guys read this. So the big contribution is inventing a loss function that kind of makes sense. Can I separate? So I cannot say what this is, but maybe I'm okay at saying, you know, can I distinguish between these two things? So, one can invent a loss function to quantify what are the interesting characteristics of the model that I want. So indeed, coming up with interesting loss functions is the game. This is where most impactful papers have been, in coming up with powerful loss functions or reward functions in RL to learn from. Indeed, that's sort of the key contribution.
Thank you so much, Dr. George.